So here we started from the Lagrangian basically and got everything in terms of the potential energy, kinetic energy, and potential energy, the matrices that give those. Instead of working with that, we could work with things which are equivalent to it, which are the correlators, QQ. I'll put the hot hats here just to remind that they're operators, QP and PP. Because we have a Gaussian state, these are, once you know these, you know the, everything's got erased out of it. Well, you know these kind of coefficients, these can be recovered from these and vice versa. So, because it's a Gaussian state, once you know the two-point functions, you know everything about the state. So it should be possible to express the answer in terms of these, and that generalizes, or specializes, that expression. That's exactly the one that Abhishek had, but it also generalizes to a space-time. In the reference I gave you of my paper, it generalizes to a space-time expression of fields. Or see, from any set of any algebra with a Gaussian state on it, even when there's quite a lot of what's the word, linear, like redundancy or linear degeneracy, a lot of linear relationships among these. See, here there's no. These are all independent. Q hat, P hat, and so on. But you could have in the space-time situation. The field values have quite a lot of dependency among them because of the equations of motion. Anyway, I said it very fast, but we could discuss it later. But it's a, so it would, if you go and look, if you go and look at the formulas in either of those two papers, you'll see that the formula I just gave you has an extremely similar appearance to the one that you find in that paper. And it would be a nice problem to relate them. They must be, in the end, really equivalent. So it must be possible to get the one derivation from the other. That would make a nice problem. So, okay, so let me take, so we have 3 minutes for questions. That thing's a little fast. Actually, we have 4 minutes for questions.
What is the problem?
Just to relate the expression that I just gave in the box here to the kind of expression that you would find in that other paper.
The Goa talk.
Yeah, for me it was a Go talk, and for them it was.
But that will fix all these parameters in the Gaussian, so you understand.
Well, yeah, so once you know V and G, then all the parameters are fixed in the Gaussian. But I just what the derivation we did was just, as I said, very straightforward. We just computed the density matrix, found out what it was, traced out the other oscillators, found its entropy, and so on. Instead of doing all of that, you could have, at the very early stage, you could have said, let's start again from the ground state. Let's find out what are these correlators. That's really a trivial step. It takes almost no work at all. And then plug those correlators into the general formula. Could you show that you would get exactly this expression following that route? That's the problem. So it's just checking, if you like, it's asking you to check the consistency between two different derivations.
This derivation was for KMS states.
This was for the ground state. So the ground state is coupled oscillators. It's not a KMS state.
And the one you wrote.
The one, and this one, I don't think it's fair to call this reduced density matrix for oscillators that one a KMS state either. Maybe it is with the right definition of an entropy.
You wrote that.
Every density matrix that's a full rank is a KMS state for some. But as a step, I mean, so every density matrix almost is a KMS state for some Hamiltonian. But this particular KMS state that I used was a step in the derivation. I did consider a thermal density matrix of a single degree of freedom, and its KMS state, and used its entropy. But I haven't used it it's not used in any physical sense that I can think of, that this reduced density matrix is a KMS state. But what's used very heavily is that it's a Gaussian state.
Quasi-free.
I think that's, yeah, that in field theory terminology, I think. Well, it's not a pure, I don't know what a quasi-free state, it's not a pure state, right? It's a mixed state, so I don't know if that's called, anyway, it's Gaussian.
Is there any other questions? Because we can just move it outside after this. I mean, these correlators will correct the stiffness of the spring, for instance. It's like,
This one, yes.
yeah.
Yeah, this governs the stiffness of the spring and which springs are connecting which oscillators to each other. So that each oscillator has its own spring, and then between every pair of oscillators, potentially, there's also a spring.
You said practically any state is a KMS state.
Yes,
You said it.
I think so.
It's almost never true.
No, for some
Hamilton. No?
No.
In fact, if I
You
had
can use
dimensions,
two-by-two matrix example where it is not true.
let's see, we have half a minute.
Yeah.
Yeah.
So you started from the ground state, but I guess as long as the reduced density matrix is Gaussian, you can still do this, right?
Yes, as long as it takes that Gaussian form, then
So you don't need to start from the ground state.
we didn't need to, right? So that's true. Along the way, we solved a more general problem, but the case of interest, most interest, for the many situations,